Okay, thank you. So, first of all, I want to thank the organizers for giving me the opportunity to talk about my blog. I'm currently a postdoc in Heidelberg, but what I'm going to present today is basically what I did in my PhD, which was part of Liverpool and part at ACES. So we were trying to model the limbs of red supergiants using interferometry. So I'm going to do like a very quick overview on the modeling situation of red supergiants, and then I'm going to go a bit more in depth into our modeling approach. So first of all, I think I don't need to spend much time.
Can I just interrupt you for a second? Do you think you'd maybe be able to have a look at your microphone? We're getting a fair bit of feedback, so I'm not sure if you can swap that around on your computer.
Oh, I don't know. Like this is better, or
that sounds better.
Now?
Is that good? Yep, that sounds perfect. Thank you.
Okay, wait. Okay, is it better now?
Yep, that's great. Thank you.
Okay, thanks. So, as I was saying, very quick overview because I guess everyone here knows. But basically, why are massive stars important, right? So massive stars, they have higher mass than 8 solar masses. They are in the upper side of the HR diagram. And essentially, they are one of the main sources of feedback for the galaxy. They also trigger star formation. We need to know also the ratio of supernova of hydrogen-rich and hydrogen-poor supernova to get the cosmological simulations. We also need to get like the most accurate stellar track. So basically, red supergiants are important to almost all the different areas of astronomy. But here we are at the advances in cool stars. So we are going to focus mainly on red supergiants, of course. So for the red supergiants, they are already evolved stars that are in a stage preceding core collapse supernova. And the main problem is that these stars, they have stellar winds, but we still don't really understand the physical processes that trigger the stellar wind. So basically, right now, when we have to model a red supergiant, we model up to the photosphere. So it's something like what you see here on the bottom right. We model the star up to the photosphere. Then we have this material that's being ejected. So we're having an extended atmosphere that we don't really know exactly what's causing these extensions. So we leave it empty. And then we add the contribution of the dust shell because this material at some point gets cold, it gets condensed, so then we have dust. So what's the main problem? We've been seeing for this whole week, basically, it's been mainly focused in AGV stars, so low and intermediate mass stars. And then we know that for these stars, they have pulsations, they have a very big convective region. And basically, these pulsations trigger the material, and then there's some dust. And then we think that the dust-driven winds is the main trigger for the acceleration of the wind for these intermediate mass stars. However, red supergiants, they are way hotter, they are way bigger, and which means that pulsations alone, they are not enough to levitate the material, and they are not enough to explain this stellar wind. So we cannot reproduce for now the extensions that we see in the red supergiants. So of course, there's been some initial modeling efforts from the community. Initially, we were thinking maybe the alpha wave-driven winds, maybe there's some magnetic fields that can actually kick out this material. You can see here, for instance, this is a plot from this attempt of the alpha wave-driven winds where we get the different velocity, the different radial velocities and then also the densities. And then they found out that actually that was not enough to kick out the material. Then they thought, okay, maybe the alpha waves, when then there's some dust that's actually dumping this material, and it was again not enough. And also the convection and the radiation pressure on the molecules have increased the opacity, so they could provide an extra kick. But again, we don't really know what's causing this extension of the material. So now there's some promising results by Key et al. On 2021, where they think that this the turbulent pressure in the star, it's enough to kick out part of this material. And then there's, of course, this 3D hydrodynamic studies that we've seen by Bernd Freitag, like the group in Uppsala. There's also the group and from Andrea Chiavassa, but the main problem is that they can reproduce the star, but they are not extending it like enough. I think it's like around 2 stellar radii or so. So what happens at the rest of the star, basically? So this was the theoretical approach, but then in parallel we also get our observations, right? And then we want to fit the observations to the data. So then there's this small sphere where basically what we do is we add the contribution of molecular layers around the photosphere of the star. So this is because depending on the wavelength that we're observing, we're going to see that the star appears larger. So you can see, for instance, here, this is the intensity that we are seeing. And then as we increase, and as we add some molecular layers around the star, we can see that it gets extended. So this is, you can see it here even better. Basically, the upper panels, you see the 1D, the reproduction of the star. And then this is the flux with respect to the wavelength. And down you see like the same thing, but basically just the intensity with respect to the radius. And as you can see at the beginning, when we have the flux of 1, we are checking the photosphere, so we're going to observe the photosphere of the star. But then as we change the wavelength range and we're having some features, our intensity changes. And then this means that we are having actually elements that are being produced in the extension of the atmosphere. So by including these molecular layers, we can actually reproduce what we are observing. So the thing is that we are including these layers, but with our new modeling approach, what we are doing is we are naturally reproducing the layers of the atmosphere without having to include them artificially. So this is our model, which is like a very really basic 1D model. We start with a MARCS model, and then we extend it up to 8 stellar radii. So basically, this model is based on observations of Betelgeuse from this model from Harper, where they got the mass continuity expression that you can see here in the middle. We assume a fixed mass loss rate, then we have the density of the wind and the velocity. So basically for the velocity, we are using these observations of Betelgeuse, and Harper came up with this semi-empirical expression where we have, it's basically like a beta law for the density. So we have gamma and beta, which are these two parameters that will tell us how shallow is the density. And you can see on the right, there's first the density, where we have the initial bump. I don't know if you see my cursor, I guess. But we have the initial bump, which is the MARCS model, and then we are just plugging in this effect of the wind with this beta law. Then for the effective temperature, it's the same thing, but here we have two different profiles because the first one is simple relative equilibrium, so it's just the temperature decreasing with radius. But then for the observations of Betelgeuse, they found out, I mean, the stars, red supergiants, they have chromospheres, and we expect that the temperature is going to increase in the chromosphere. So basically, we are using two different models, this with relative equilibrium, which is just the temperature decreasing, and then the Harper model, which is the one where we have a bump, so the temperature increases at around like 1 stellar radii. So initially, this model was developed by Dan Davis and Bertrand Pless, and they mainly focus on the effect of the model in the titanium oxide bands. So you can see here, this is in the optical region, and you can see for the bands, in black, we have the MARCS model, and then as we increase our mass loss rate, we see that our titanium oxide bands get more prominent. So this model could explain, as I already said, all the features that we get from the Mole spheres. So there was no need to get like these artificial molecular layers around the star. And what was also very interesting is that we could reconcile the effective temperature determination methods in red supergiants. So just a little bit to talk about this. So basically, there's different ways to get the effective temperature of red supergiants. The one that's the most commonly used now is fitting the titanium oxide lines, because these are the most prominent lines that we find in red supergiants. But we found out, as you can see here on the right, that actually when we fit the titanium oxide bands only with MARCS models, so without including any wind, we get a temperature that's super cold. And then they found out that we could also fit, instead of the titanium oxide bands, we could fit the line-free near-infrared continuum region, because in this line-free region, this region was formed in the photosphere, which means that actually we were getting hotter effective temperatures, and we could actually reconcile it with the evolutionary models. So the main point is that the titanium oxide bands, they are not formed in the photosphere, but they are formed in the extended regions. And the MARCS models, they don't take into account the extended regions. But if we include the wind, we can actually reconcile both effective temperature determination methods. So we have our model. And then we plug it into turbo spectrum, which essentially solves all the radiative transfer equations, and it's going to give us the intensities with respect to the line of sight and also the fluxes. So you can see initially what we get with the intensities. This is for like one case of our model. On the top left, this is the initial MARCS model. As I said, it's a 1D model. Of course, it's very approximate, but you see that for MARCS, there's no extension at all. We have up to 1 stellar radii. And then as we increase the mass loss rate, we are actually filling the emptiness. So we're like extending our atmosphere naturally. Again, it's a 1D model, but you will see later that it works pretty well for now. So what we are doing now is we are just filling this emptiness that I said that initially we just don't really know how to explain the extension of the wind. So we have this model that can actually start filling the extended atmosphere. So then we get the intensities, and we integrate it over the whole line of sight, so we can get the spectra, right? So for the spectra, this is a case for the KL and M band. So we are going here to the infrared. We are not focusing anymore on the titanium oxide bands. And you can see there's some features here, especially water and carbon oxide and SiO. And initially we have in yellow, this is the MARCS model. But what happens when we increase the mass loss rate? So we already see something happening in the spectra. So for the CO lines, this is the case of relative equilibrium. So this is the case where the temperature is just decreasing with radius. So we are not taking into account this chronospheric temperature inversion. But for now, what we see is, especially, so for the CO, the lines are reproduced almost the same as with MARCS. But especially if we go into the L bands, so around 4 microns or more, we can see that interesting things start to happen. So essentially, we're going to have CO and SiO in emission. And we also see, for the cases like a very extreme mass loss rate, we also see already a difference in the water. So now we can go a step further because we have interferometry. And interferometry gives us a really high angular resolution, which means that we can really observe this extension of the atmosphere of red supergiants. So basically, I guess everyone knows here, but interferometry, we are using an array of telescopes. We are increasing the effective area of our telescope, which means, again, we're getting higher angular resolution. And what we obtain, since we're just getting the interferometry of light, we're just getting the visibilities. So the visibilities, physically, they don't make much sense because they are in the Fourier space. So we have to transform them to get the intensities, which is something that it already makes more sense for us. And it's this expression that you see here. So we have data from AMBER, from Gravity, and from MATISSE. And later I will tell you, like with this data, how it relates to our models. So this is, again, only the model. So here, for now, we are not showing any data. So what happens with these models? We have the intensities, which means that we can obtain the visibilities. And basically, you can see, compared to the flux, here, the changes are way more dramatic, right? So you see in yellow, again, is the MARCS model, where there's no features at all, because the MARCS model is not extended. But as we already increase our mass loss rate, so we are extending the atmosphere, we already see extension especially in the CO. You can see that the lines get more prominent, and especially in this area that I was saying, the L band, you can see a lot of things happening. So this As I said, physically, it's a little bit hard to understand the concept of the visibility, but it gives us basically an idea of how extended is our model. So as you can see, if we see more features, it means that it's going to be more extended. So as I said, we have a model with this beta law. So we have some gamma and beta parameters that initially we fix because we use the same as Harper, but we can of course play a bit with these parameters. And this is going to be important, especially for the profile in the density. So you can see, especially for the region near the photosphere, that's going to be important. And near the photosphere is where the water lines are formed. So this is interesting when we want to fit the water lines in our observations. So we also, we played a bit with these parameters to find the best fit of the gamma and beta. And then, if you remember at the beginning, I said that we also use two different profiles on the effective temperature. I was showing you all the results with the red case here, where it's the temperature decreasing. But what happens when the temperature increases because of the effect of the chromosphere? So you can see these are the two different models. On the upper side, on the upper plot, you can see the flux, and on the lower plot, you see the visibility. So basically, the main difference here is that in the 2.5 microns, for the chromospheric temperature inversion, so for the Harper profile, we see CO in emission for the flux. And this is something that in the observations we don't see at all. And already with a very low mass loss rate, we can see even like CO really depleted or like already in emission. And if we check, for instance, like a very extreme case of like BY Canis majoris, not even then we see CO in emission. So this means that we think that for this wavelength range, at least, our observations are well better explained only with this relative equilibrium case, so with the temperature decreasing with radius. So this was a little bit shocking for us because we were expecting that the temperature increases in the chromosphere, so we were expecting that in our wavelength range we would see this increase and that this blue profile would fit better our observations. But then there's this lukewarm chromospheres theory that says that basically, so at the same radius, we're going to have different substructures in the temperature, which means we're going to have different, at the exact same radius, different temperatures. And we think that depending on the wavelength range that we are observing, we're going to be sensitive to these different temperatures. So there's already also a lot of studies that are like working on this. And we see here some examples, for instance, for the optical and for the UV, we are sensitive to a temperature of like 5,000 Kelvin. So we have a way higher temperature than the one that we are observing in the infrared, for instance, which is around 2,000 Kelvin. And also, again, in the radio, the temperature that we are sensitive is, again, different than for the other wavelength range. So this is basically complicates everything more, which means we cannot just assume one simple profile for the temperature. We have to take into account which wavelength range we are observing. And now I'm going to go to the comparison with data, because all of that so far has been theoretical with the model, but what happens when we go into real data? So the very first step, which is kind of like a parenthesis here, is to compare with the most simple model that we can find, which is the uniform disk model. This is just like a spherical model of a star, but this is just to fit our visibilities. So basically, it's this very simple model for the photosphere, and then we try to fit the best angular diameter. And then we see, this is the case for the different data of some red supergiants that we obtained. Essentially, we have the best fit angular diameter depending on the wavelength that we're observing. So you see that it's not the same all the time, so the angular diameter changes. And this is just to give you an idea of that if the angular diameter changes, it means that our lines are formed in the extended region of the atmosphere, basically. It's just a little parenthesis that I made here to see like what we can first check without getting into our models. So essentially what this is telling us is that we are forming the elements in the different wavelength ranges, we are forming them in the extended atmosphere. Then we got data from, the first data that we got is from AMBER, and AMBER is from the J, H, and K band, so it's again in the infrared. This was data that was already published, so we got initial issues data that was published by Arroyo Torres. And what happens when we check the data? So here we have one case of a red supergiant. You see the two upper panels are the fluxes, and then the two lower panels are the visibilities. So you can see in gray, this is the data. In orange is the MARCS model, so the initial model without any extension. And then in red is our best fit model for this star. So you see when you check both fluxes, both panels that you see up here, basically everything coincides. So the data, the MARCS model, and our model is almost the same, which is actually great because the initial paper of this data is using MARCS. So if it would not be the same, we would be a bit worried. But then what happens when we go to the visibilities? So especially focusing on the CO, you can see that in yellow is the MARCS model, which has no features at all. And in red, we are fitting for the very first time the CO extension, which is something very exciting. So if you compare it with the gray and the red, you can see that actually it fits pretty well compared to the initial models. So, of course, there's also water. And as I said, water is formed closer to the photosphere. So basically, it's going to be more sensitive to these beta and gamma parameters of the density profile. So then this was already published data, but we also got our own data of brand new red supergiants that were not observed. And we have gravity. With gravity, basically, we are getting the K band, so from 2 to 2.4 microns. We have a really high resolution, spectral resolution. And you can see these are the results with gravity for AH Scorpii. In gray, again, we have upper panel the flux, lower panel the visibilities. In gray is the observations. In red is our best fit model. And in green, you can see the MARCS model. So as you see, I think there was kind of a problem with the normalization of the MARCS model here, but as you can see, our model fits the flux pretty well. And the important thing is when we go into the visibilities, because the case of MARCS, there's no extension at all, so it doesn't fit at all. But when we are when we are using our model, we are fitting again for the very first time the CO lines. But again, we are going even further because we have MATISSE data also. And MATISSE goes to higher wavelengths. So we have L, M, and N data. So as I said, the L data, which was around 4 microns, was pretty interesting. If you remember at the very beginning that I said the 4 microns, there's the SIO line. So we can now finally compare with the SIO. So for this, we are only using L and M data because the N data is way affected by dust. So as I said, our models don't include the dust contribution. So for now, we maybe plan to extend it. But yeah, we're just gonna plot the L and M data. So you can see this here in the upper panels again. That's the flux for L and for M. On the lower panels, there's the visibility, and you can see again in green is the MARCS model, in red is our model, and it's especially interesting at the 4 microns because the flux changes in this wavelength range compared to MARCS, and we can see that actually our model fits way better the SIO. And especially for the M band, again we have the carbon oxide, which is way better reproduced by our model than with MARCS. In this case, the difference is even more striking, I would say. And then for the SIO, we also have, we can reproduce also the extension, and you can even reproduce this emission that we have here. So finally, I want to talk a little bit more of the SIO because we know that it's a precursor of the silicate dust formation. So basically, with our models, we can see that first it is formed at the extended atmosphere, as I was saying. And you can see here on the left, there's the partial pressure of the SIO with respect to the partial pressure, with respect to the pressure of the gas, and then the intensity with respect to the intensity of the continuum. And this for the different red supergiants that we were that we had data. And you can see basically the important takeaway from these plots is that from 2 to 3 stellar radii, we see that the intensity decreases of SIO. And then beyond 3 stellar radius, it becomes constant. And also it's the same with the pressure. And this means essentially that beyond 3 stellar radii, all the silicium is already associated with the SIO molecules. And this is something that's already in accordance with other papers, so just for instance, Guile in 2020.
Gemma, you've got 5 minutes.
Okay, because, yeah, I'm done. So basically the conclusions is that our model can reproduce for the first time the extension of the atmospheres without having to include the mole spec layers. So it naturally reproduces the mole spec molecular layers. We've had interferometric data for the infrared, so for the K, L, and M band. And basically, well, we see that the radiative equilibrium can reproduce better our profile, our spectra, and this is because when we include this bump in the temperature from the chromosphere, we're going to have the CO in emission, which we don't really observe in our observations. And this could be, I mean, this is true for this wavelength range, but as we said, it could be that in the optical or in the UV, we would have to get a higher temperature in the chromosphere to reproduce the lines. Then we also observe 5 red supergiants with gravity and MATISSE. And so far, this is one of the most complete spectro-interferometric studies of red supergiants up to date. And we're covering a very wide wavelength range from 2 to 30 microns, even though the N band from like 5 to 30 microns, I didn't show because it's heavily affected by dust. And then finally, limitations, because of course this is first of all, a 1D model is extremely approximate. And second of all, you may have noticed that the mass loss rates that we are getting are really high. And they are, so what we think is, it could be because we're having a MARCS model that it's really compact. So what I'm trying to do now is I'm trying to compare with other models that I already got with some extra extensions and then plugging in the effect of our win. And then we see that we can reconcile better the mass loss rates. So yeah, I think that's everything. Thank you.
Hello, thank you for the great talk. I have 2 questions. The first one is, what's the lowest surface gravity star that you modeled?
Oof. No, I don't remember. I mean, minus 0.5, I guess.
Okay, cool. Thank you. And the second one was, does any of your modeling allow you to comment on how polarized these extended atmospheres are?
No, because so I know that for gravity you can get also some like different polarizations, but we didn't use that, and so far, no, it's not.
Okay, thank you.
All right, Ursula?
Hi, is there an evidence that there's a range in mass loss rates in red supergiants where some of them are extremely high and others are more, let's say, commensurate with what we believe they should be?
Actually, well, so first of all, I think measuring the mass loss rate on the red supergiant is already pretty hard. And we've seen, I think, for the D1 Canis Majoris, which is one of the most extreme ones, I think it's 10 to the minus 4, and it's pretty high. But usually, for the ones that we have measured, they are way lower. And since, I mean, the mass loss recipes, they give us different ranges, and it's like a mess. Yeah, so yeah, we don't really know exactly like what are the correct mass loss rates, but from the ones that we measure, I think so far they are lower. So yeah.
Hi, Gemma. Thank you for a very nice talk. I had a very small question about the 1D MARCS models you were extending in research. Is there any significant difference for your synthetic spectra if you start with plane parallel or spherically symmetric model atmospheres?
Actually, that's a great idea. That's a great question. But no, I think so far we tried and it doesn't make much of a difference, though.
Hey, Gemma, KU Leuven. I had a question since indeed the MARCS models are not really made for supergiants, since, you know, this, as you correctly said, they are 1D. But now you add in an empirical way more and more material, right? Small spheres. But isn't that just not what you, just a sign of it's a 3D complex thing where we have these different temperatures, at one optical depth roughly, etc., etc. So where will we end? And you can always add extra 3 parameters in your model, but at some point, you know, then we have the elephant that we can fit with everything. So what is then the end goal?
But you mean like the end goal of our models, or?
Yeah, since I can easily see that you can have a model that fits one red supergiant and potentially the same model a second one, but each of them will have different inhomogeneities, different filling factors for all of the material that you put in. But
so as
I can see the parameters that you can easily add in to have the data fitted. But we aim for the physical understanding. But so how many free parameters will we then still add in?
No, but so our models, we don't model the dust. So we cut the model at 800 kelvins because otherwise the turbo spectrum goes crazy. So so far I was thinking it would be actually interesting to include the dust to make it even more extended and see what happens. But I guess it would get way more complicated with all these extra free parameters, as you were saying. But for now, we have our model is super simple and it doesn't include any dust.